During the last decades, the winds of the low mass load rate oxygen-rich AGB stars have been studied in detail by means of single-dish and interferometer observations. However, the envelopes of low mass load rate carbon stars are poorly known so far. In this talk, we present the results of our last work on this type of objects, focusing on the J-type star Y Canum venaticorum. In the envelope of a typical AGB star, parent molecules such as CO, HCN, C2A2, or SIS form close to the stellar photosphere and are radially accelerated, with the rest of the gas one's refractory species form dust grains, and radiation pressure pushes them away. These parent molecules are dissociated at hundreds of stellar radii by the galactic UV radiation field, triggering a very active chemistry that produces a plethora of new molecules. The region of the envelope where circumstellar chemistry develops for low mass load rate carbon stars is expected to be quite smaller than for high mass load rate stars, due to the lower dust opacity, producing molecules with different abundances. Furthermore, it is still poorly known how similar are the matter rejection mechanisms working at low mass load rate carbon and oxygen-rich stars, since they can be in different evolutionary stages. As a first step to answer these questions, we have observed HCN toward the low mass load rate J-type star YCBN in the mid-infrared and millimeter wavelength ranges. The mid-infrared observations were taken at 7.5 and 14 microns with the EXIS spectrograph, which is mounted on SOFIA, that flies at altitudes about 35,000 feet, and at 13.1 microns with the TEXIS spectrograph at the IRTF. Additional data at 1.12 millimeters were acquired with the IRAM 30-meter telescope. Low spectral resolution observations taken with ISO were used to describe the continuum emission. The mid-infrared observations show spectral ranges crowded with lines of HCN, C2A2, and CS. About 130 lines of HCN and H13CN were detected involving lower levels with energies up to 3900 Kelvin. The EHCN lines at 14 microns display PCD profiles with very strong emission components, whereas they are completely in absorption at 7.5 microns. The lines are quite broad, with local light widths up to 10 km per second at the photosphere. Pure rotational lines of HCN and H13CN were detected in the millimeter range, involving levels with energies up to 2000 Kelvin. The profiles of these lines are substantially affected by kinetic and excitation effects, and some of them display maser spikes. The intensity of H13CN lines suggests a low 12C to 13C isotopic ratio. The spectral energy distribution of YCBN can be described by a central star at 2900 Kelvin, warm to hot silicon carbide dust, and cold amorphous carbon dust. This third component is needed to explain an emission excess found beyond 15 microns. Several molecular bands are noticeable at different wavelengths. The infrared HCN lines can be described with four thermal populations with rotational temperatures between 100 and 3300 Kelvin. Lines observed at 14 microns are sensitive to rotational temperatures below 1300 Kelvin, and those at 7.5 microns better trace hotter HCN. These data sets imply substantially different column densities, which means that they could be tracing gas with different properties. We modeled the observations with a radiation transfer code, assuming a spherically symmetric envelope. It was not possible to reproduce data at 14 and 7.5 microns simultaneously with the same envelope model, supporting our findings derived from the excitation diagram. The pure rotational lines are compatible with the envelope model derived from the observations at 14 microns. We proposed a possible 2D scenario that could explain this disagreement. We found that there should be an HCN abundance or gas density increase in front of the star close to the photosphere. The gas density and rotational temperature is needed to be anisotropic, and the gas expansion velocity field complex. Outflows expanding at velocities higher than the commonly accepted terminal velocity might exist. To summarize, YCBN is a low mass load rate star with a thin circumstellar envelope, which seems to be affected with high turbulence close to the photosphere or violent matter ejection mechanisms. The envelope can be asymmetric, and the gas expansion velocity field and the physical and chemical conditions complex. The HCN abundance is quite high compared to that of IRC 10216, usually considered as the archetypal carbon-rich AGB star. The isotopic ratio 12C to 13C is about 2.5, which is compatible with previous measures. Several questions arise. Is YCBN a peculiar star, or are the asymmetries common in envelopes of low mass load rate carbon stars? Have they anything to do with the J-type character of YCBN? In case you are interested in reading the whole paper, you can find it by following any of the frame links. Thank you.